Welcome to this lecture. We're going to talk about the cross product, its properties, and as a simple application, we're going to talk about the area of a parallelogram, or actually the area of a triangle. So we're going to see both. Now, we're going to do something which is going to be quite analogous to what we did in the case of a dot product. We're going to give two definitions. One of them is going to tell us what's going on with the cross product, what exactly it is. And the second one, but it's going to be hard to use for computations. And the second one is going to be very, very simple for computations, but it doesn't going to give us, it's not going to give us any insights into what the cross product is. So one of the things that we should note here is that unlike the dot product, which can be defined for any dimension, the cross product is exclusive to 3 dimensions. So suppose that U and V are 2 3-dimensional vectors. Then their cross product is denoted and it is also a 3-dimensional vector. And as I told you, we're going to give 2 definitions. So let's see what the 2 definitions are. So imagine that you have the 2 vectors u and v in 3D, and you force them to originate at the same point. Okay. Then what will happen is the vector u cross v will be is perpendicular to the plane spanned by the vectors u and v, which means that we have some kind of problem if the 2 vectors do not span a plane, and we're going to explain what happens in this case. And its magnitude is equal to the magnitude of u times the magnitude of v times the sine of the angle between the 2 vectors. The angle between the 2 vectors is exactly the same one that we discussed in the case of the cross product, I mean, in the case of the dot product. So it's an angle somewhere between 0 and pi. Please notice that for those angles, the sine is a non-negative quantity. So the product that I just wrote down is going to be non-negative. So it can be used as a length for a vector. And there are 2 things that this description that I just gave you leaves out. The first thing is, what happens if the vectors u and v are not spanning a plane? And when does that happen? It happens when they're parallel. If they're parallel, then they're really lying on one line, and you cannot define in a some straightforward way, a plane that contains those two vectors. In fact, there will be infinitely many planes that contain those vectors. So in that case, the cross product is 0. So let's say that if U is parallel to V, then the cross product of U and V is equal to the 0 vector. Okay, so nothing interesting happens, or rather it's the most straightforward case. The second thing that this definition leaves out is, okay, we're given that the vector is perpendicular to the plane formed by the vectors U and V. Where does it point? Because once we know what the magnitude is, and the magnitude of this vector is this much, the question is, we have two choices. So which of the two choices is it going to be? And for this, there is a rule that one could actually describe using fingers. We're not going to actually do any of those things. For the specific case that I'm showing you here, I think the right choice, at least from the perspective that I see it, the right choice would have been downward like this. So this is where U cross V would be pointing. But the bottom line is that we will never want to find the vector this way. We will have the second way that will give us the vector. And in that case, the vector will be pinned down completely without any need to define its direction. Now, to give you an idea about how things are pretty much going to work here, let me just say that the vector I, when you take the cross product with the vector j, you actually take the vector k. So if you took the vectors I, j, k, and you try to pretty much adapt your fingers like that, and then apply them to the specific vectors that you're looking at, then you would be able to actually guess what the direction of the cross product would be. And there are other empirical rules that involve the motion of a screw that is moving in the right direction. But like I said, there's no particular need to go in any detail over any of those particular methods, since this is how we're going to define the way that we will actually use ultimately in order to compute the cross product. So imagine that you have two vectors, U with coordinates U1, U2, U3, and V with coordinates V1, V2, V3. And then their cross product is defined by this formula that might look a little strange at first, but we're going to explain it, and then you're going to see that it's going to be very, very simple. So U1, U2, U3, V1, V2, V3. So the object we're looking at is called a determinant. And we're really going to use the expansion of this determinant with respect to the first row. So here I might as well take a moment to tell you how a generic 3x3 determinant is expanded with respect to its first row. So if you have a determinant like this, A1, A2, A3, B1, B2, B3, C1, C2, C3, then to expand it with respect to the first row, to get a number, supposedly here, all the quantities A1, A2, A3, B1, B2, B3, C1, C2, C3 are numbers. Then you take the first entry of the first row, A1, and then you try to imagine what will happen if you delete the first row and the first column. So imagine that you delete the first row and the first column, then you come up with a 2x2 determinant, which is what? It's B2, B3, C2, C3. And now you continue by pretty much doing the same thing with the second entry of the first row, but you use a negative sign here. So you put minus A2 times the determinant that you get by deleting the first row and the second column. Again, try to visualize what will happen if you delete the first row and the second column. And you will realize that you get B1, B3, C1, C3. And finally, you will do plus, and you will again have to visualize what happens if you delete the first row and the third column. So here you will put A3 times B1, B2, C1, C2. My apologies. It seems that I keep pressing the button for the new page. So that's what it is. Okay, and of course here I should remind you that the 2x2 determinant is defined by multiplying the numbers on the main diagonal. The main diagonal is the one that goes from the upper left corner to the lower right corner times the minus the elements, the product of the elements in the other diagonal. So it will be A1 times B2C3 minus B3C2 minus A2 times B1C3 minus B3C1, and finally plus A3 times B1C2 minus B2C1. Okay, so now how do we apply this in the case of our gross product? Let's go back here. And what we have is, so if we delete first row and first column, we will get the determinant U2, U3, V2, V3 times the vector I. For the vector J, we will use a negative sign. In the middle term, we always have a negative sign. We should note here that determinants are highly alternating objects, so meaning they involve same amount of pluses and minuses. So you will get, so if you delete the first row and the second column, you will get U1, U3, V1, V3 times J. And finally, plus, and now delete the first row and the third column, and that will give you the determinant U1, U2, V1, V2 times K. And if you put all this in one vector, then on the first coordinate, you will get U2, V3 minus U3, V2, comma, minus U1, V3 minus U3, V1. And the last component will be, the last coordinate will be U1, V2 minus U2, V1. At first, it might look, the whole operation might look a little involved, but once you do it a few times, then you will get the hang of it. And let's get started. Let's do some examples. So let me give you not I, let's call it U. We said I is reserved exclusively for 1, 0, 0. So let's say U is 1, 3, negative 2. And V is 2, 1, negative 1. I should pay attention not to give you parallel vectors. If I give you parallel vectors, then I mean, it's okay. The formula that we just found will give us the 0 vector, but you know, we want to have something slightly more interesting. So here, obviously, you can see that these two vectors are not parallel using the argument that we have discussed before, meaning you cannot really scale the vector u in order to get this vector v. If you had to do that, then by looking at the first coordinates, you would guess that you have to scale it by 2, but then that doesn't work for the other coordinates. So anyway, pause the video, and try to compute u cross v. I'm setting it up here, actually. You might want to look at the part where I'm setting it up, and then just pause the video and try to do the computation. Again, let me give a disclaimer that it is possible that there are some numerical errors that will regretfully appear in these lectures, but hopefully they will be easy to correct, to spot and correct. So pause the video and try to find what the cross product is going to be. Okay, so let's see what it's going to be. So I have to first delete the first row and the first column, and this will give me the determinant 3, negative 2, 1, negative 1. For the middle determinant, it goes with a negative sign in front. I delete the first row and the second column, and that is going to be 1, 2, negative 2, negative 1. And for the last vector, I delete the first row and the third column, and that will give me 1, 3, 2, 1. And now I compute this determinant. So the first one is negative 3 minus negative 2. So negative 3 plus 2, that's negative 1. The second one is minus 1 plus 4, that's 3. With a minus in front, that's negative 3. And the last one is 1 minus 6, that's negative 5. And hopefully, if I haven't committed any numerical error, then that's precisely the cross product of u and v. Okay? Why don't we do one more? Why don't we do one more? Like I said, it's something that most probably many of you see for the first time. So let's say that we have 2, negative 1, 4, and v is 1, 3, negative 1. So please go ahead and find the cross product of u and v. This time I'm not going to set it up for you. Pause the video. I'll give you a couple of seconds and then try to do it. Okay, so let's see how it's done. So u cross v is going to be I, j, k. And then you will have 2, negative 1, 4. We will have 2, negative 1, 4, 1, 3, negative 1. If you want me to do this computation by using I, j, k, so it will be delete first row and first column. That will give you minus 1, 4, 3, negative 1 times I, minus delete first row, second column. So that will give you 2, 4, 1, negative 1, j. Delete first row, third column. That will give you 2, negative 1, 1, 3, k. And let's do this computation. So the first one will be 1 minus 12, that's negative 13 times I. The second one is negative 2 minus 4, that's negative 6. With the extra negative, that's plus 6j. And the last one is 6 plus 1, that's 7k. You can leave it like this, or as usual, you can write it as minus 13, 6, 7. And that's it. Okay. Now, let's list the properties of the cross product. So what do we have? Well, the first one is that the cross product is not commutative. In fact, if you change the order of the two vectors that are being multiplied, that are being crossed, if you like, then you get the opposite vector. And it's not associative either. But it's still bilinear. And here I should write actually the properties for both coordinates. So u1 plus u2 cross v is u1 cross v plus u2 cross v. And lambda u cross v. Now I could put them all together. So I could first write that this is lambda times u cross v, and you could also put it in the second coordinate. So lambda, not lambda, rather u cross lambda v. And I should note that it's also the nice distributivity holds for the second coordinate. So u cross v1 plus v2 is the same thing as u cross v1 plus u cross v2. Then we also have that this is what we said, the premise that we gave in the very beginning, that u cross v is perpendicular to both the vectors u and v. In particular, it's perpendicular to any vector which is a linear combination, meaning you scale u and v any way you like, and then you add them up. The cross product of two vectors is the zero vector if and only if the vectors are parallel to each other. And of course, this includes the case that one of them is the zero vector. The magnitude of the cross product is the product of the magnitudes times the sine of the angle between them. And here we should say that this is identified with a very specific number through simple trigonometry. This is the area of the parallelogram spanned by u and v. So let me spell it out what I mean by this. So imagine that this is the vector u, this is the vector v, and this is what I mean by the parallelogram spanned by the two vectors. So the area of this parallelogram is exactly equal numerically to u cross v, to the magnitude of u cross v. Okay. And of course, that means that if you have two vectors and you want to compute, instead of the area of the parallelogram, you want to compute the area of the triangle that is formed by these two vectors, then that area is going to simply be 1/2 of the magnitude of the cross product of the two vectors. Okay. Then finally, we can say that we can argue that the magnitude of the cross product of two vectors is equal to the product of the magnitudes, if and only if the two vectors are orthogonal to each other. Yeah. This is the case where everything works out perfectly. That's because the sine of pi over 2 is equal to 1. Okay, and that really, there's one property that I would like to add. It's not that we're going to discuss, but it's such a beautiful property that I would like to discuss. So imagine that you have three vectors. right? So when you have three vectors, so you have, let's say, the vector u, you have the vector v, so immediately these two vectors form a parallelogram, right, this way. And now you get a vector w going like this. And by using this vector, you form what is known as a parallelepiped. A very interesting word. Okay, it's a skewed box if you like, so this is called the parallelepiped. Formed by UVW. It turns out that the volume of this parallelepiped this has volume which is equal to the cross product of U and V, right? And then you take the dot product with W. The only problem is that you don't know whether this is going to be positive or negative. Just to be on the safe side, you take the absolute value of this. And it turns out that numerically, this is going to be simply a determinant. So if U is U1, U2, U3, and V is V1, V2, V3, and W is W1, W2, W3, then this volume is simply the absolute value of this determinant, U1, U2, U3, V1, V2, V3, and W1, W2, W3. There's another magnificent property here that says that it doesn't matter in what order you take this. So if you take U cross V dot W, then that's the same thing as U dot V cross W. Sometimes people call this the mixed product of three vectors, and its value is simply the determinant without the absolute values. This is just for your encyclopedic pleasure. We're not going to use this in any of the things that are going to follow, and that's why I'm putting this property in a parenthesis. Okay, so there are some interesting problems that one can solve using the tools that we have just developed, and pretty much the most typical problem in this case is to find the area of a triangle spanned by that has given vertices. So find the area of the triangle with vertices (1 to -1), 3 to -5, and 1 4 2. Okay, so how do we do this? The idea is pretty simple. I will not make any attempt to guess how these points are located in space, but I'm going to call them A, B, and C. So points A, B, and C, and I'm going to generically draw them. I'm not saying what I'm drawing should be taken to bear any particular resemblance to the proportions of the distance between those points. But let's say, for the sake of the argument, that this is the triangle whose area we wish to compute. The idea is pretty simple. Form two vectors, so A, B, and C, and take half of the area of the magnitude of the cross product. I'm sorry, half of the magnitude of the cross product of those two vectors. Okay, so the area of triangle is going to be 1/2 of the magnitude of AB cross AC. And let's see what it is. So what is the vector AB? The vector AB is, I'm going to subtract the coordinates of A from the coordinates of B. So it's going to be 2, 0, and -4. And the vector AC is going to be 0, 2, and 3. So I would like to take the cross product of these two vectors. Two, 0, -4, and 0, 2, 3. At this point, somebody might ask, can we use any other combination of points? And the answer is yes. As long as you don't take AB and BA, for example, as long as you take two vectors that contain all 3 points, you're going to be fine. Okay, it doesn't matter how you take them. So what do we get here? So delete the first row and the first column, and you will get 0 times 3 minus -8, which gives you an 8 on the first coordinate. On the second coordinate, you get a 2 times 3, which is 6, but it's the middle coordinate, so that becomes -6. And on the last coordinate, you get 2 times 2, which is 4. So this is the cross product of the two vectors. The magnitude of the cross product is square root of the square of 8, which is 64, plus the square root, the square of -6, which is 36, 100 so far, plus the square root of the square of 4, which is 16, and this is square root of 116. You can simplify this a little, but it's besides the point. So the area of the triangle, which is our final answer, is going to be 1/2 square root of 116. I mean, by using simple algebra, you can simplify it if you like. So, you know what? Why don't I do it so that we can see how it's done? I mean, you need to divide 116 by 4. It's what, 4 times 29. So this is 1/2 times 2 square root of 29. And of course, this would give you square root of 29. And that's it. Okay. A simple cancellation, simplification, which is actually quite redundant and you don't need to worry about it. Okay, there's some other really cool things that we can do with the cross product. So one of the things that we're going to be doing pretty soon is use the cross product in order to find vectors that are perpendicular to a given plane. So we're going to use this all the time. And in this respect, let me do the following example, which could be quite nice to consider. So here's another example. Find all unit vectors that are perpendicular, orthogonal in other words, to the plane containing the points 2, 1, 3, 1, 3, -5, and 2, 3, -1. Okay, so you can pause the video and try to think about it, try to do as much as you can. Let me just say that there are not too many vectors, you might think to yourself that there are way too many vectors to list, but let me warn you, there are not too many vectors that have these properties. Okay, so I'll pause for 2 seconds. And here's how we can solve this. So it's pretty much the same story. We want to go from points to vectors. So let me name these points. The idea is that if you have the plane that contains these points, then to find a vector, to begin by finding a vector which is perpendicular to this, you can just take the cross product of AB cross AC. Okay, that's the idea. So what is AB? It's going to be -1, 2, and -8. And what is AC? It's going to be 0, 2, and -4. Okay, so what is AB cross AC? There's a little trick that could make our life a little easier. You see, do I need to have 2 times -4? I mean, all I need is I could take half of AC to make my life easier. I could take the vector 0, 1, -2 and come up with slightly smaller numbers. But it will not be a problem if we do it without thinking too much here. When you look for just a vector which is perpendicular to a plane spanned by 2 vectors, you can just scale those vectors as much as you like and make them much simpler. But in any case, like I told you, it's not going to be a problem. So in any case, let's take delete first row, delete first column. So we will have -8 plus 16, that's 8. Delete first row, delete second column, that will give you a 4. It's the middle one, that will be a -4. Delete the first row and the third column, and that will give you a -2. So this is the vector. So guess what? You just found a vector which is perpendicular to the plane. All you need to do is normalize it and also take its opposite. So here's where there's this little old trick where it tells you if you have a vector to normalize, then you can normalize any positive multiple of the same vector. And in particular, this is 2 times the vector 4, -2, -1. So instead of normalizing 8, -4, -2, you can normalize this vector and you will find the exact same thing. Okay, if you think about it, it's as if you have 2 vectors that are not just parallel, but they point to the same direction, and you want to find the corresponding unit vector that does the same thing. And it doesn't matter which one of the 2 you're going to normalize. You will always get the same thing. So if I normalize for -2, -1, to do so, I need the magnitude of 4, -2, and -1. And this is square root of 16 plus 4 plus 1. So I take the squares of the numbers 4, -2, and -1. So that gives me square root of 21. And so that will produce the vector 4 over square root of 21, -2 over square root of 21, and -1 over square root of 21. And I should just take plus or minus. These are the only unit vectors that are perpendicular to the given plane. Okay, and in particular to the plane that contains these 3 points. Okay, very, very interesting exercise. And I have one more. And this one, before we do this exercise, I would like to give you a simple property that connects the dot product with the cross product. Now, you have to be careful here. The dot product is a number, the cross product is a vector, but still, you can find the connection between them. And the connection is the following. If you take the dot product, which is a number, and you square it, and then you take the cross product, always of 2 3-dimensional vectors, and you take the magnitude of the cross product, which is now a number, and you square it, then you find the magnitude of u squared times the magnitude of v squared. And this is the reason for this, if you think about it, is nothing else but the Pythagorean theorem in its trigonometric form. Because if you think about it, this will end up being the magnitude of u squared times the magnitude of v squared times cosine square of theta. And this will be nothing else but u squared, magnitude of u squared times magnitude of v squared times sine square of theta. When you add them up, cosine square plus sine square gives you 1, and you will pretty much get this thing. So, but this is the formula that is interesting to remember. And I'm going to formulate an exercise based on this formula. So I'm going to say the following. Two unit vectors, u comma v, or you know what, let's not make them units. So two vectors u comma v are such that the length of u is 2, the length of v is 5, and u dot v, what can I choose for u dot v? Any number between 10 and -10. Why? Because the dot product is magnitude of the first times magnitude of the second times cosine, and the cosine is going to be between -1 and 1. So I'm randomly choosing 4 here, and I'm asking you to find the magnitude of the cross product of the two vectors. Okay, so this is the problem. And can you do it by using the relation that I just gave you? So again, pause the video and give it a try. And then try to do it yourselves. Yeah. Well, I hope you did it. So let's see how it's done. So basically, if we are to apply the above formula, then what are we going to get? We're going to get the dot product square, which is 4 squared, plus u cross v all squared, is equal to the square of the magnitude of u, which is 4, right, since the magnitude is 2, times the square of the magnitude of v, which is 25, since the magnitude is 5, right? So this will give you that u cross v squared, so you have 100 minus 16. That's the same thing as 84. And eventually you're going to get that u cross v is equal to square root of 84. And that does it. That's a very nice little exercise. Of course, once you take this formula for granted, which again boils down to the Pythagorean theorem. I keep saying Pythagorean theorem because pretty much this relation here can be thought of as the Pythagorean theorem, since it really describes what happens for a triangle that has hypotenuse 1. If the hypotenuse is 1 and this angle is theta, then this is sine theta, this is cosine theta, and the Pythagorean theorem is really cosine square plus sine square is equal to 1. Okay, so a lot of interesting things. So things have become much more geometric with the introduction of the cross product. The cross product is going to play a very important role in what is going to happen in this course. There are some very, very interesting things that we're going to be able to do using the cross product, mainly finding vectors that are perpendicular to given planes or surfaces for that matter, and that is going to play a very important role later. And that brings us to the end of this lecture. Thank you so much for watching.